Mathematical paradoxes are fascinating brain teasers. Was Epimenides, a Cretan and a semi-mythical philosopher, lying or telling the truth when he said that all Cretans are liars? In network science, things are often not as they seem, and in this video we explore the friendship paradox and how it can be used to detect and control infectious diseases. Infectious diseases are responsible for 32% of deaths worldwide, with the biggest challenges in the poorest parts of the world. Inventing cheaper ways to detect and combat disease, especially in the most vulnerable areas, is key. Infectious diseases are spread through contact between individuals via air particles or through direct physical contact. It's sort of like a meme spreading through a social media network. If we look at social networks like graphs, we can see who's in contact with whom. In practice, we probably don't know precisely who's in touch with whom or where the edges and joints of the graph lie, but we may know something about its probability distribution. A probability distribution assigns a probability to a particular outcome. For example, when rolling a die, each outcome has a probability of 1 out of 6. These probability distributions also describe networks. Networks come in many different forms. The simplest model is the Erdos-Renyi network, where each possible edge is drawn with a fixed probability. However, when modelling the spread of infection on such a network, epidemiologists and social scientists noticed that this model didn't describe real social networks. Other network models, such as the preferential attachment model, better show how disease is spread through a social network. This model draws links depending on the existing number of links a point has, just like how the rich become richer. One thing we're certain of: vaccinations stop infectious diseases. But if we can only afford to vaccinate a limited number of people, or if a very infectious disease needs to be stopped quickly, who should be targeted? Ideally, we'd aim for the hub in the middle of the smaller networks, as they have contact with the most people. But how can we identify who these hubs are? If we randomly vaccinate people, it's highly unlikely that we'll be successful. The friendship paradox says that on average, your friends have more friends than you do. This is because if we pick a random person and ask them to name a friend, they're more likely to name someone who knows lots of people, rather than someone who only knows 1 or 2 people. This means that vaccinating a randomly selected contact of a randomly selected person will be more likely to hit the hub node and extinguish the epidemic. This was shown to work a few years ago when a group of college students was vaccinated against the flu. Even if we aren't interested in vaccinating and just want to track the spread of a disease or even a particular fashion, the friendship paradox can be used for that purpose too. The Cost Action Cost Net consists of a collaboration of more than 500 researchers across 34 countries and is funded by the EU to carry out research into network data science. Our research is, for example, crucial to understanding and controlling infectious diseases, but also the stability of global financial networks, novel drug targets in genetic networks, as well as underreporting in arms trade networks.